Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the electronics engineering. Today in this video, we are going to talk about the full wave rectifier. First of all, we will see what is a full wave rectifier, then we will see its structure, right, its block diagram and its operation also we are going to see. After that, we will see its waveform and the different types of analysis of its parameter, like we are going to have the analysis of DC current and IC current in this video itself, and in the upcoming video we will be talking about the further parameters related to the full wave rectifier. So let's start our discussion with the introduction to the full wave rectifier. What is a full wave rectifier? As the name suggests, we get the output across the load for full cycle of the input signal. What was the problem in the half wave rectifier? Only when the input was in positive half, so at that time only we were getting the output. We were not getting the output when we have the negative signal, right? So now here we will be getting signal for both of the components of the input, for the positive half as well as for the negative half, right? So we get the output across the load for full cycle of the input, right? We will never get a zero signal like we were having the zero signal in the half wave rectifier. Now I can classify the full wave rectifier as the full wave rectifier with the center tapped transformer, and in this video first we will be talking about the full wave rectifier with the center tapped transformer only. In the next video we will be talking about the full wave bridge rectifier, right? First of all, we will have a full detailed analysis of the center tapped transformer full wave rectifier. Then we will move towards the bridge rectifier. We will see what is the problem with it. Then we will move towards the bridge rectifier. So this is the circuit for the full wave rectifier. Here again we are supplying some AC voltage, 230 volt and 50 Hertz frequency, right? This is my transformer. This is a step down transformer. As I told you, in the half wave rectifier we were using the one diode. Here we will be using the two diodes, right? So here you can see we have one diode over here and one diode over here. So we have two diodes over here, and now we have connected a load resistance also over here, and now we have a center tap transformer. So we have a tap at the point O, which is at the center. Now this is point A, this is point B. I hope you understood the circuit really well. We are taking the output from the load resistance, so we will be taking the parallel output from this, and the parallel voltage to this load resistance will be my VL, right? So I hope you understood all of them. Here we will be using the two diodes, diode D1 and the diode D2, which will be used as a switching element, right? We know the diode is going to conduct in only one direction. In the forward direction only it is going to conduct, in the reverse direction it will be an open circuit, right? So we will be having two diodes which are going to conduct in the two different waves, right? When I have positive half of wave, one diode will conduct, and when I have negative half of wave, the diode D2 will conduct. And this is how we have made the circuit. So one diode acts for one half of the cycle and second diode the other half of the cycle. So we will be having two diodes which are acting for both half of the cycle, and in this manner we can get full wave at the output. So now here we will be using the center tapped transformer, and which will be becoming a problem later on, and I will be telling you how, right? So now this is the operation of the circuit. For the positive half cycle, first let's understand the operation, then we will be understanding the operation for the negative half cycle. Here we have the transformer, we are supplying the input. Now when I have the positive half cycle, at the A terminal I will be having the positive, right? So here I will be having negative. Now here if the negative terminal is connected to the P terminal of the diode, you can see here we have the P terminal of the diode, here also we have P terminal of the diode. So when negative is connected to the P terminal, diode will be in reverse bias, it will be acting as an open circuit, diode D2 will become open. Now when the positive terminal is connected to the P side of the diode, diode will be a closed circuit, right? So here it will be behaving like a perfect conductor, and it will be giving the full current to pass through it, right? So now here due to this voltage, due to this plus minus voltage, I will be having some current flow. So current will flow in this manner, right? So here when the current is flowing in this manner, across RL I will be having some current. So when the current flows across the resistor, it will be generating some load voltage. So the terminal A is at higher potential than the center terminal O. Terminal B is more negative than the center terminal O, right? So terminal B is at negative potential and terminal O is at positive potential, right? If we compare terminal B and terminal O. Now diode D1 will become forward bias and diode D2 will become reverse bias. Diode D1 will be in on state because it is in forward bias and it will conduct, it will give the path to the flow of the current, whereas diode D2 block the path of the current and it will be in off state, right? So the current flows through diode D1 and RL will be the load voltage from where I can calculate the VL, right? So I hope you understood how in the positive half cycle I am going to get the voltage across RL. Now coming to the negative half cycle. So what happens in the negative half cycle? In the negative half cycle, I will be having A terminal more negative as compared to the O terminal. O terminal will be positive as compared to the A terminal, right? Here I have the negative half cycle. Now, when I have A terminal, which is negative terminal connected to the P side of the diode D1 will be now in the open circuit and it will be in the reverse bias. Thus, it became the open circuit. It will stop the flow of current, and now here the terminal B is at a more positive potential than the terminal O, and this is the reason when the terminal B is at more positive potential, it is connected to the P side of the diode and it is going to make this diode a full conductor and the current can easily pass through this diode. So now here current is passing through this path, it will move upside here and from here it will again move towards the RL load resistance, and when the current is moving in the RL load resistance, it will be generating some voltage VL, right? So here terminal A is at the lower potential than the center terminal O and terminal B is at the higher potential than the center terminal O, and because of which diode D1 become reverse bias and diode D2 becomes forward bias. D1 becomes off, thus behave like an open switch, you can see over here, and D2 becomes forward bias, thus becomes on and it will start conducting and current flows through the diode D2 and reach up to RL, and thus a voltage generates at the RL which can be represented as the load voltage. I hope you understood the operation. So this is the waveform that we have, right? So this is the waveform that we have supplied, which is having the maxima Vm and it is having the duration 2 pi, right? From 0 to 2 pi it is completing one complete cycle. Now you can see here we have one more wave. This is the opposite of this wave, right? So this is the wave which is at the A terminal, VAO, and this is the voltage which is at the B terminal, right? So now at the B terminal I will be having the negative of the wave which is present at the A terminal. You can see over here. So here I have negative positive, here I will be having negative positive. So point B or the terminal B is exactly reversed from the point A. So whatever wave we have at the A terminal, I will be having the opposite wave at the B terminal, right? Now when I have the positive wave, so when I have VAO, it is going to turn on the diode D1 and we will be having ID1, the current due to the diode D1, right? And again here we have the positive, so again here we will be having current due to the diode D1. Now here you can see we have the positive VB and due to which the diode D2 is turned on and we will be having the current due to the diode D2. So overall if I see the full current, if I combine both of the current, because I will be getting the load resistance and the load voltage at the same terminal, at this instant of time I will be getting this current, at this instant of time I will be getting this current, after this I will be getting this current. So if I combine both of them I will be getting the current like this and the maxima is Im. Again I can represent the voltage also, you can see the voltage is represented like this, and for the full wave I am getting the output voltage. So I hope you understood the voltage waveform. So now coming to the representation of the output. Input voltage is Vm sin omega t. So the load voltage can be represented as the same as the input voltage, which is Vm sin omega t when we have 0 to pi, right? So when omega t is in between 0 to pi, the load voltage is Vm sin omega t. But when the omega t is from pi to 2 pi, I will be having the reverse of the input voltage. At the B terminal I was having the reverse of the input voltage, so I will be having minus Vm sin omega t, right? So similarly I can represent the load current. Load current is equal to Im sin omega t for 0 to pi, and it is equal to minus Im sin omega t from pi to 2 pi, right? Similarly I can represent the voltage and the current. Now what is Im? Im is related to the Vm. In the previous video also, when we were talking about the half wave rectifier, we talked about the relation between the Im and Vm. So Im is equal to Vm upon the total resistance. What is the total resistance over here? Load resistance plus forward resistance plus R2, right? So here R2 is the DC resistance of the secondary winding of the transformer, right? So now coming to the two types of current that we have, average current and the RMS current. So our average current is also known as DC current. So here we remember the formula. It is 1 upon upper limit minus lower limit, which is 1 upon 2 pi integration from 0 to 2 pi I d omega t, right? Now here I have to use the current equation that we have over here. So the current equation is different from 0 to pi, and it is different from pi to 2 pi as well. So for 0 to pi I will be using the first current equation. I will be using 1 upon 2 pi integration from 0 to pi. I have Im sin omega t d omega t. From pi to 2 pi I have minus Im sin omega t d omega t. So this is my second equation. Now I can easily integrate both of them. Im is a constant, I can put it outside. So Im upon 2 pi I will be having integration of sin omega t is minus cos omega t, and here integration of minus sin omega t will be equal to cos omega t. So you just need to put the limit 0 and pi to 2 pi. So I will be having Im upon 2 pi minus cos pi plus cos of 0 plus cos of 2 pi minus of cos of pi. So I will be left out with 2 Im upon pi. So this is my IDC, right? So IDC can be represented in the terms of Im, and I know what was Im. Im was represented as Vm upon the total resistance was RL plus RF plus R2, right? So we can put this value of Im over here, and I can get 2 upon pi Vm upon RL plus RF plus R2. So this is how I can represent the average DC load current for the full wave rectifier. Now coming to the RMS AC load current. So what is the RMS AC load current? For the RMS, we already know the formula, root mean square. First of all I will be taking the root, so this power 1 by 2 represents the root. Now mean, for mean I have 1 upon upper limit minus lower limit, so we have 1 upon 2 pi. Now I will be taking the square. So now here I will be having 0 to pi Im square sin square omega t. So I am taking 1 upon, I will be representing it over here, IRMS is equal to 1 upon 2 pi. Now here I will be having 0 to 2 pi I d omega t, right? So I square I have to take because it's a root mean square value, and the power is 1 by 2. So power is 1 by 2, which means root. 1 upon 2 pi means mean, and here I square means square, right? So this is how I can put the value of I square. I square is different from 0 to pi and from pi to 2 pi. So from 0 to pi I is Im sin omega t, so I square would be Im square sin square omega t, right? From pi to 2 pi it was minus Im sin omega t, its square would be again Im square sin square omega t. So now here I can put the value of sin square as 1 minus cos 2 omega t upon 2, and I can pull out Im. So here I will be having Im upon 2 pi power 1 by 2, and here this is Im square, and here I will be having integration from 0 to pi 1 minus cos 2 omega t upon 2 d omega t, plus from pi to 2 pi I have 1 minus cos 2 omega t upon 2 d omega t power 1 by 2. So when you solve this, and I am leaving it on you, you can solve it. It's very simple integration that you can solve. Pull out your notebooks and do some task, solve it. When you will solve it, IRMS will come out to be equal to Im upon root 2. So now again I can put the value of Im. Im was equal to Vm upon total resistance RL plus RF plus R2. So when you put value of Im over here, you will be having 1 upon root 2 Vm upon RL plus RF plus R2. So this is how you can represent the RMS AC voltage or the RMS AC current as well. So now I hope you understood all of the things that I have discussed in this video. If you have any doubt, you can put the doubt in the comment and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel, share it with your friends and also give me your feedback. Thank you so much.